So this problem deals primarily with probability, and specifically it gives you a Poisson distribution, and you also have to know some things about binomial distributions. So for Poisson distributions, you need to know the differences between your CDFs and your PDF, and your CDF is cumulative. You need to know when to use each one, so when you should use cumulative or PDF, and also how they're interchangeable, how you can change between them. You also need to know how to manipulate the Poisson equation specifically, which is shown right here, where the probability that x is equal to number is m to the x, e to the negative m over x factorial. And mainly you need to know how you can change the mean to solve a problem. For the binomial distribution, mainly you just need to know how to identify a binomial distribution. And you know anything is a binomial distribution when you have two outcomes, and only two outcomes. You have a number of trials to reach one of these outcomes, and then you also have a constant probability, and then you're possibly looking for a desired amount of successful outcomes.
Okay, so for A, we're trying to find the probability that there are no arrivals in a given half-hour period. So we were given the mean equals 1 every 10 minutes. But in this case, we're looking at a half-hour period, which is 30 minutes. So we're going to multiply this by 3, which gives us 3 every 30 minutes. All we have to do is substitute this into a problem. So our mean was 3, x is 0, e to negative 3 over x factorial. Now you can solve this out, or you can put this into our calculator, into our Poisson PDF, as shown, and our x is going to equal 0, and our mean is 3, as stated, which is going to give us the answer of 0.0498.
So for part B, we're trying to solve for a nurse who works for a 2-hour period and find the probability that there are fewer than 10 casualties during this period. So we're going to need to manipulate the mean, or the mu. So for 2 hours, we're going to have a mu of 12 because for 120 minutes, that's 12 10-minute intervals, and because one casualty occurs every 10 minutes, we're going to get a mu of 12 casualties in 2 hours. So from there, we're going to set up our Poisson distribution with our mean, or mu being 12, and our distribution being less than 10 casualties, which is the same as or inclusive of 9. As shown on the number line, we're going to be looking for any value of 9 and below, assuming we're looking for those casualties and anything below it. So we're going to set up a CDF, because CDF gives us this, and it will include the 9 and below. And because CDF is inclusive, we're going to choose the 9 value as our point of inclusion. We're going to set up our mu, and we're going to use this as a function in our GEC active calculators. And we're going to get, when we solve it, 0.242 is the probability that less than 10 casualties will occur in a 2-hour period. So for part C, we're going to have to find 6 nurses working a consecutive 2-hour period between 8 a.m. and 8 p.m. We're going to be finding the probability that no more than 3 nurses have to attend to less than 10 casualties during their work period. So we're going to be using a binomial distribution here. This is important to note because you can see it because we have a set number of trials, which is going to be our 6 nurses, and we have a constant probability, which we found in the previous problem, which was 0.242, probability of having to less than 10 casualties. And our probability that less than or equal to 3 of these nurses are going to have to attend, which is going to be our x, or our desired number of outcomes. So because we're GEC active, again, we're just going to use our function, our calculator. We're going to have a little binomial CDF action in here. And we're going to plug in our values of n, which is 6 for 6 nurses, our probability, which is 0.242, and our desired number outcome, which is less than or equal to 3 nurses. And when you solve that, you will find that 0.966 is your desired, or the outcome probability of this.
So part D of the problem asks you to calculate the time interval during which there's a 95% chance of there being at least 2 casualties. So it's using the same parameters as the first 2 parts, so we're going to be in a Poisson distribution, and it says at least 2 casualties and 95%. So what we're going to be looking at is that the probability that x is greater than or equal to 2, so at least 2, is 0.95. But another way that we can look at that is that the probability that x equals 0 plus the probability that x equals 1 would be equal to 0.05, because 0.05. Because if greater than or equal to 2 is 0.95, then everything besides that, so 1 and 0, is 0.05. So we're using Poisson, so you're going to have the standard equation, m to the x, e to the negative m over x factorial. So normally, our x is 2 because we're looking for at least 2, but what would our m be? And if you think about it, if you have a casualty or someone arrives every 10 minutes, then for any given time period, your mean would be t over 10. For example, in a 60-minute time period, you'd have 6 casualties. That's t over 10. But if we substitute m for being the number of 10-minute intervals instead, then you would get a neat t equals m. And that's going to be a lot easier because when you substitute that into the equation, everything will come out a lot smoother as opposed to having t over 10. All right? So if you come over here, you'll go back to the p that x equals 0 plus the p that x equals 1 being equal to 0.05, and then we're just going to substitute everything into this equation. And here you have x being 0 and x being 1. And when you simplify that all down and you solve for t, and you can solve for t in any number of ways because our GDC is active, you get time being 4.74. But if you remember correctly, we said that t is actually the number of 10-minute intervals, so our true time for which the probability that there is 2 casualties is 95% is 47.4 minutes.